Welcome back, everyone. Now that we understand the theory and intuition behind decision trees, we're going to focus on learning how to code decision trees with Python and scikit-learn. In part 1 of this series of lectures, we'll be focusing on the actual dataset as well as feature engineering off that dataset. Let's head to the notebook and get started. Okay, here I am at my browser. I've gone ahead and imported NumPy, Pandas, Matplotlib.pyplot, and Seaborn as SNS. Let's read in our dataset, which is known as the 𝑃𝒉 dataset. We'll say df is equal to pd.read_csv, and underneath your data folder, you should be able to read in data, and then there's two penguin files. The one we're working with is penguins_size.csv. Go ahead and run that, and then if you run df.head, you should be able to see the actual data set. Now, the 𝒂𝒉 dataset is basically a data set containing a bunch of features of penguins and then their associated species. So we have the actual species of that penguin, and if we take a look at df species column, we can actually ask for the unique species. And there are three unique species here: Adelie, Chinstrap, and then Gentoo or Gentoo. And those are the species that we want to be able to predict. So we had some researchers visit these islands, and they categorize the penguins to their correct species, and then hopefully in the future someone else can just, based off the features of the penguins, categorize them to the correct species. So if we take a look at the actual features, we have the island feature, which are the different islands available for these penguins to be found on, and then we also have flipper length, body mass in grams, then we have sex of the penguin, male or female. Notice we do have some missing data in this data set, so we'll have to perform a little bit of feature engineering. And then we also have the culmen length and culmen depth, which is essentially just another word for the beak of the penguin. And we can check out the bill dimensions, which are the bill length and bill depth in the raw data. They're recorded as culmen length and culmen depth. So you can check out the 𝒂𝒉 dataset official page. Just Google search 𝒂𝒉. Lots of interesting things about this particular dataset. But what we want to do is just do a little bit of feature engineering to figure out if we have any issues with the dataset before we actually begin learning about it, and then later on in a future lecture performing a decision tree to classify penguins. Now what we're going to do is first check out how many missing data points we have. We can do that by checking df is null. Recall that's going to return true or false if something is null, and what we really want is just a sum, which is going to treat false as 0 and true as 1, which means it's going to report back how many missing values you have. So notice that it looks like we have two missing values for culmen length feature, two missing values for culmen depth feature, two missing values for flipper length feature, again, and then 2 for body mass in grams. And then 10 of those penguins are missing their sex. Now if we take a look at the actual information, or df.info, we have 344 entries. So we can be pretty flexible over trying to fill in these features based off what we already know on the other features, or if we should just drop them. Now we did see in this quick example up here in the head of the data frame, you should have noticed that one of these penguins is essentially missing all their features. It only knows the island they were from. So this is probably a good penguin to just drop from the data set. Let's go ahead and explore what would happen if we just say df.dropNA. So I'm going to say df is equal to df.dropNA, run that, and then check df info, and this is essentially the most extreme version of getting rid of these null values. So instead of trying to fill them in through some sort of other calculation, we'll just drop any rows that have missing values. And if you notice, we still end up with 334 entries versus the original 344, which means that these 10 rows that were missing the sex of the penguins also included what were essentially 2 rows that were missing pretty much everything else. So in reality, there was going to be 2 rows that there was not really appropriate approach we could take to fill in that missing value set, because it was missing information on essentially all the features. Like we see up here, there's not any good logic to use to try to fill in these features unless you were trying to fill in the average values for all these continuous numerics and then just take a guess at the sex value. But in reality, it's better to just drop this row because there's essentially no information here beyond the actual label and one feature. As far as the other 8 rows that were missing sex values, it could be reasonable to try to fill in those values based off the other features, but given that we're actually not dropping that much of the data itself, we're only dropping an additional 8 rows, it's just easiest to go ahead and drop that data. If you want, you can later on explore the actual statistical methods to actually try to fill in those sex values based off things like the known weight of the penguin, which is a totally valid approach as well, and would help you keep some more of that data. Now, the last thing we should do here as well is explore the categorical features to make sure there's no mistakes with any of the categories we're considering. So if I take a look at 𝑑𝒂𝒓𝒄𝒄 again, notice I have the species label, island, and then if we go all the way to the right, I also have the sex. So let's explore what unique factors we have in the island feature. So we'll say 𝑑𝒂𝒓 island unique. And there I can see that there's 3 unique islands, Torgerson, 𝒂𝒃, and Dream Island. And now let's also check 𝑑𝒂𝒓 sex unique. And for this, I have male, female, but you'll note that one of these rows actually has sex equal to this dot. So if we take a look at 𝑑𝒂𝒓, where 𝑑𝒂𝒓 sex is equal to dot, there seems to be essentially kind of some bad information here where we don't know this particular sex of the penguin, but we do know everything else about that penguin. And we also know that penguin's species. Now, something we can do is just drop this row, essentially grab everything but this row and continuing with the dropping. Or what we could also do is try to figure out what is the most likely sex of this penguin, especially if we know its body mass grams. One way we can try to figure this out is by comparing this to the average male and female in our data set for this particular species of penguin. We'll say the following. Go ahead and grab off this data frame where species is equal to this particular species of penguin. We don't want to compare it to species of penguin that it's not related to, just this particular species. And then what I'm also going to do is, once I'm done with that, I'm going to group by sex so that I have females and males separated. And I'll also have this sex separated of this dot sex where I don't have the information. And then I'm going to call describe, which is going to grab a bunch of statistical information per sex. And if you just run describe, it gives you this layout where you have this multi-level index as the columns, so 32 columns. It's much easier to read if I transpose this. So I will say dot transpose and then run this. And now what I have are the standard deviation, mean, minimum, and max values. I can directly compare my features for the unknown sex and then male versus female. Let's take a look at the beak measurements or the Coleman measurements, that is Coleman length and Coleman depth. I can see that my unknown row has a value of 44.5. Notice it doesn't have a standard deviation because there was only one value. And so all these values are saying min, max, etc. There's just one row represented. It looks to be a little closer to the female average. So I have a mean of 44.5 and I'm leaning more towards the Coleman length of the female. And it looks like standard deviation for these are pretty close, 2 and 2.7. So males tend to have a longer length and I'm more aligned with female. So that's kind of 1 point to classifying this as female. Now if I continue along this, I can see Coleman depth. And then Coleman depth, it looks like my value here for my particular unknown was 15.7. And that's actually right in line with the male average instead of the female average. And if we take a look at the standard deviations, 0.54, but we can also see that the max value for a female was 15.5, where the max value for a male was 17.3, and the minimums were 13 and 14 for female and male respectively. So again, recall it goes dot female male here. And I would encourage you to run this code and actually check this out yourself. So this one is leaning a little more towards male. So now we kind of have 1 point for female, 1 point for male, but it's not unreasonable to say Coleman depth is possible of 15.7 for a female, given the fact that we have already a max value of 15.5 for a female of this penguin species. Next, we can take a look at flipper length. Our flipper length value was 217, and this is actually right in the middle of the average value for a female at 212 or a male at 221. And if we take a look at the minimum values for the male versus female, as well as the max values, the males tend to have a little bit longer flippers. And this one looks to be a little shorter than the average male. So I would kind of say this is leaning more towards female, but again, a little hard to say because it's right in the middle of these average values. So there's definitely flippers that are 217 millimeters for both females and males, leaning a little more towards female on this one, but hard to tell. And then finally, probably the one that's most telling is going to be body mass in grams. Our particular penguin had a body mass of 4,875. And if we take a look at the average female, it's 4,679 with a standard deviation of 281. The male is 5,484. So the males are quite a bit heavier than the penguin that we have. And the lightest male in our data set is 4,750, with the heaviest male being 6,300. And notice the heaviest female is 5,200. So this is quite a bit lighter penguin, and it looks like in general we would have already at 4,875 a pretty light penguin. Now there was a male that weighed 4,750, but that was kind of an outlier. We can see immediately as we jump to the 25% quartile, it goes to 5,300, already much heavier than the penguin we have. So based on all of this, I would lean towards female, although I could definitely see the argument that this is an outlier male, given that it does happen to land in a lot of the male mean categories. But for my take on this, it leans closer to the female data points, considering the mean, standard deviation, and the min and max values, than it does towards the male points. So now let's go ahead and relabel this row as having a sex of female. The easiest and most robust way of doing this is to use the .at method. It's similar to .loc, except the issue with .loc is it will actually assign a value to a slice of a copy of a data frame. So it won't actually affect your original data frame. It's harder to reassign it. So when you want to actually change out a single cell value, specifically I want to change out the value for the cell here, dot, where the column is sex and the index value is 336, I can use the at call for this. Notice that it uses square brackets. So the way it works is df, and I say at, and then in square brackets, I'm going to pass in my index. So it's going to say grab the index, and my index is actually 336. And then it's the sex column. And I set it equal to whatever I want. So I'm going to say female. So you run that, and if you take a look at that row again, so df loc of 336, notice the sex has now been reassigned to female, and it's the same body mass grams that we saw earlier for that particular penguin. And that's probably the most robust way of doing this and making sure you don't get any warnings or errors of the setting a copy to a data frame that we've seen before. Now, if you want to visualize this, there's lots of different things we can compare this to. I'd recommend right off the bat, it's a small enough data set where we can say SNS pair plot, pass in the data frame, and explore the actual label we're trying to categorize, which is species, and then run that. And you should be able to see a nice pair plot show up where you can begin to see just how separated out these species are. And in general, it looks like for some of the features, we can actually get pretty good separation between the three species of penguins. So we would expect our decision tree algorithm, or really any machine learning algorithm, to perform quite well on this data. There is some overlap between this Adeline chinstrap species on things like their flipper length versus the culmen length or culmen depth here, but there is enough information that we're getting some pretty nice separation on these classes. And if you want, you can do a scatter plot to zoom in closely on one of these, call a scatter plot of any of these two features. What I would also recommend doing is something like an SNS cat plot. So this is the generalized thing like a box plot, where we can compare, let's say, species on X versus culmen length. So we'll say culmen length in millimeters on Y, and we have to say the data that we're considering. And since I'm saying cat plot instead of something like box plot, I have to specify the kind of categorical plot. And this is where you could say and start experimenting with different plot types that we've explored in the Seaborn section. But I can say kind is equal to box here. And what's nice about cat plot is that while I can run just a generalized box plot like this, I can also begin to define columns. So I can say separate this out on columns of sex, run that, and I can begin to compare on the columns sex is equal to male versus sex is equal to female, again for culmen length of the various species. Lots of different visualizations you can perform here, but I leave it up to you to continue to explore this data. What I want to do now is make sure my data is set up correctly for the decision tree. Now, a quick note for decision trees. We saw in the theory and intuition lectures that a decision tree in theory should actually be able to take in multi-categorical data. For example, if we take a look at df islands, or island, there were multiple categories that were strings. Because of an implementation feature for scikit-learn's decision tree, and in fact you can check out at the time of this filming, this is actually still an open pull request. Right now, it does not support multi-categories being passed in as strings. Hopefully in the future, you will be able to pass these in. It will essentially do an automated label encoder to categorical encoder, and this is what this pull request is asking for. But this pull request has been kind of open since 2018, and there is an eventual idea. They keep working on it, closing it, etc. But keep in mind that for right now, we do have to create dummy variables for things that are multi-categorical like df island in order to pass it into a decision tree. Even though I mentioned in the theory and intuition lectures that we shouldn't actually need to do that, but we will have to do it for the way it's implemented in scikit-learn. So keep that in mind. I'm going to have to actually say pd.getDummies. And the fastest way to do this is to actually just pass in my features. So I'm going to say pd.getDummies of df. And you'll notice if I say pd.getDummies of df, it's actually going to do it for a species as well. So it gives you too many columns. If we scroll all the way back here, it also has the, whoops, maybe I scrolled a little too further. Let's go over here. Here we go. It also has the species, Adelie and Chinstrap. I just want to do this for my features, not my actual species. Features, or excuse me, labels are okay to keep as their original strings, Adelie. So what I really want here is df drop species along axis is equal to 1. So now I'm essentially only doing this for my x data points, my x features. So Coleman length, Coleman depth, flipper length, body mass grams, those are not changed because those were numeric continuous features. What I had to change were my categorical ones. So now I have Island Biscoe, Island Dream, Island Torgerson, sex female, and sex male. Now, as you recall from previous discussions, we actually don't need to keep all these columns because encoding sex female will automatically encode sex male since I only have female and male options. I know if female is 0, then it must be sex male. And we also have seen that I can simply say drop first equals true to get rid of this. So if I say drop first equal true, it will automatically drop that first row. Okay, or first column, excuse me. And that means we're essentially ready to go. What I'm going to do is kind of formalize this into my x features. So say x is equal to this, and then my y is simply equal to the df species column. Now, unlike other machine learning algorithms, recall what actually happens in a decision tree node. It's going to directly compare the entire data set on a single feature. It's going to say, is this feature equal to this particular category? Or is this feature less than or equal to this particular number? Which means I actually don't need to perform any sort of feature scaling since I'm never going to be using multiple features at the same time. I don't actually care if one feature is in a way different scale than another because as I flow down that decision tree statistical learning chart, I'm actually just comparing just a single feature along a particular range of values. Which means what I can do is directly off x and y, skip the scaling process, and go straight to the train test split. So we'll say from sklearn dot model selection import train test split, call train test split, shift tab, and expand on this until I can see right here what I always do, copy and paste this tuple. And then scroll over to the right. And just to be in line for everything, we'll say test size is, let's say, 0.3 and a random state of 101. And if you want to get the exact same results we do, go ahead and use the same test size and random state. Okay, so we've explored the data, we fixed the data a little bit, got rid of some missing features, and now we're ready to go into part 2, where we're actually going to perform the decision tree classifier and build it out with scikit-learn. I'll see you there.